if we look at history, models of the brain have always been the most fashionable technology. It was hydrodynamics in the 17th century, and digital computers a few decades ago, and 10 years ago was convolutional neural networks, and now transformers, of course. So in preparation for this, we have an introduction to transformers. I think this is something that Michael Fee, chairman of this department here, and Jim DiCarlo asked for. Of course, they are not here, but Michael actually asked me to record it. Is that possible?
It's recording now, as long as that's okay with you guys.
Yeah. Cool. Everybody agrees to be recorded? Okay, all right. So with this, we have an introduction to transformers, and this probably will be the first of some of the research meeting where we'll speak about transformers. Next time, perhaps more in comparison or in the framework of models of the brain. But this time is more on just technical aspects of transformers. And so Phillip, Isola, Cecile, and Brian Cheung, this building, will tell us, oh, Jim is here after all. Okay, so lupus in fabula.
What was that?
Lupus in fabula exactly means what happened, that I was speaking about you and you came in.
Oh, the magic.
So Phillip will start. And then we have Brian, and then perhaps discussion. And in the meantime, of course, very welcome to ask a lot of questions. All right.
Okay, great. Thank you, Tommy. So this can be, as far as I'm concerned, very informal. I'm happy to go back and forth. I took slides from a lecture, like hour-and-a-half lecture on transformers I've given, and tried to pick a few slides. So it's going to be a quick intro, but we can go into as much detail as you want, and happy to make it also just more discussion. But I'll start by talking about, what are transformers, for those of you who haven't encountered them yet. Okay. So I think that there are two key ideas that are not new, but are relatively popularized by transformers. And the first is called the idea of tokens. And then the second is going to be the idea of attention. There's a few other bits and pieces in transformers, but to me, those are the two kind of key ideas. Okay, so tokens are essentially a new data structure, and they're a replacement for neurons. Okay, so in artificial neural nets, neurons are just real numbers, just scalar numbers, and tokens are vectors. So that is the distinction that, as far as I'm concerned. So it's just lingo for a vector of neurons, a vector of scalars. But when you start thinking of your primitive units in a network as tokens rather than neurons, then sometimes the math will look a little bit different. And I think it's just a powerful way of working with new kinds of neural networks made out of token-sensitive neurons. Okay. Again,
it's a patch in an image, right?
A patch in an image can be a token. I'll give a few examples, and not a new idea. It's vector neurons, vectors of features for a unit inside a network. That's an old idea. Shows up in graph neural networks if you've seen those too. Okay, but the way I like to think of it is we used to work with arrays of neurons, and now in transformers we work with arrays, tensors of various shape of tokens, but they're kind of like encapsulated vectors of information. Okay, so you can tokenize just about anything, and that is like the big trend right now, is just show how to turn whatever data you have into a sequence of tokens. So here's an example, like Tommy is mentioning, of tokenizing an image. You could do this in a million different ways, but the way that is very common is you start with an image, you break it into patches, you flatten all the patches to just take all the rows of that, those pixels, and just concatenate them into a really long row or a really long column vector. And then you get this thing called a token, which is just an n-dimensional vector representing that patch. And this arrow up here, if you can see my mouse, it could just be flatten or concatenate, but commonly it will actually be a linear projection to some fixed dimensionality. So project to a 128 dimensional vector, for example.
Should I think of a token as an embedding? Is it the same or what?
Same thing, yeah. So a vector embedding of a patch would be a token in this context, yeah. So there's a lot of names for this, but to me, like, yeah, once you start thinking of things in terms of tokens, like that's how I like to think of it. Okay, so you can tokenize anything. That's often a linear projection. We used to operate over neurons, now we operate over tokens. And just a few more examples. So whenever you can take your signal and chop it up into chunks and project each chunk to a fixed dimensionality vector, then you can tokenize that data. So for language, people do this as well. They chop up into little chunks, which are often 2 characters or a few characters at a time, and they project those into 120 dimensional vectors. With sound, you just chop up into little tiny snippets of sound. So you can tokenize anything, and once you've tokenized it, then it's just a sequence-like representation, a sequence of vectors. Although really the way transformers work is they treat it as a set, not a sequence, but people often talk of it as a sequence. Okay, so that's tokenization. I think that's the first critical idea. And then everything ends up being operators defined over tokens as opposed to over neurons. So rather than taking linear combinations of neurons, which is the common linear layer in a network, we take linear combinations of tokens where you just take a weighted combination of vectors instead of a weighted combination of scalars. Okay, so I'm not in this, because it's only like a little intro, going to go into the math in detail, but we can always come back if you're interested. Okay, so in standard artificial neural networks, there's 2 key layers. There's the linear combination layer, the linear layer, and there is the pointwise nonlinearity, which might be a ReLU or a sigmoid function. So in tokens, there's the same thing. There's a linear layer, which we have here, just a linear combination of vectors. And then there's a token-wise nonlinearity, which is completely analogous to a neuron-wise nonlinearity. So this is a neural net that does a pointwise nonlinearity over neurons. It applies the same function ReLU to every neuron in a list. And the token net applies the same function f to every token in a list or in a set. Okay, usually f is going to be itself a multi-layer perceptron. It will be some parameterized function. You can equivalently think of this as a convolution over the tokens. So transformers, CNNs, it's all the same ideas kind of rehashed. We can talk about that if people are interested. But here's what it looks like. It's just a token-wise operation that slides along the list of tokens. Okay, so you can see that looks like convolution sliding across the signal. Okay.
It's usually one layer, right?
Is it usually one layer? I think that it's usually linear, ReLU, linear. Yeah, so it's a nonlinear function. It just has to be nonlinear so you get nonlinearities into the system.
So call it MLP.
I have a question.
MLP.
One layer net.
Well, 2 linear layer MLP, but sure, yeah, you could call it something else. Yeah, question.
I have a quick question for the last slide. Like, I think I have missed. What is the Z here? Like in the last slide?
Oh, Z is the token code vector, meaning the vector of neurons inside that token. So the token has this code vector that lives inside it. Yeah.
Okay, thank you.
You're welcome. Yeah.
What's the analogy with convolution here?
So convolution applies the same operator independently and identically to every item in a sequence, and this is doing the same thing. So it's like slide the filter across. Here is slide this nonlinear filter across the sequence. But we think of it as a 1-by-1 kernel because it doesn't the receptive field in the sequence dimension is just looking at 1 token at a time. So, okay, so here's a neural net. And here is what I'll call a token net. So it's just like a neural net alternating linear combination, pointwise nonlinearity, but now it's linear combination of tokens and token-wise nonlinearity. And transformers are in that family. Another name for that family is graph neural networks. They have the exact same structure. Okay, but the terminology is just different in graph neural nets, but they're the same thing. Token nets, graph nets, transformers are all the same thing. You could say that transformers are a special kind of graph net if you prefer to look at it that way. Okay, so there's so many connections that could be made, but I'm going to zoom right ahead and we can maybe discuss all the connections. So that idea number 1 is build things out of tokens, vector valued units, as opposed to out of neurons, scalar valued units. Idea number 2 to me is attention. Maybe this is the most famous idea of transformers, is they have this new layer called attention. So let's look at what attention is. Okay, so in a neural net, or what I'm calling a token net, you'll have linear combinations of inputs to produce an output, a weighted sum of the inputs to produce an output. And you will parameterize that mapping with weights W, and those will be learnable. And in attention, you have a weighted combination of inputs to produce an output, but the parameters or the values in the matrix A are not learnable. Instead, they're going to be data dependent. They're going to be a function of the some other data. So when you have data dependent linear combination where the weights are a function of some other data, then that's called attention. Okay. And so A is the weight matrix, and it's just a function of something else. It tells you what to attend to, how much weight to apply to each token in the input sequence. And you'll take a weighted sum, which is just matrix multiply A by the tokens. Okay, notation, don't worry about it. So here's the intuition. So I can have attention given to me by some other branch of my neural network. Maybe it's going to be a branch that parses a question. And that question will tell me what patches in the input should I attend to. The input patches are represented by tokens. And I will say, these are the patches that I'm going to place high weight on, and then I'll take a weighted sum of the code vectors inside those patches to produce an output. So I could ask, a question, what is the color of the bird's head? I'll attend to the bird's head. What is the color of the vegetation? I'll attend to the background. It's just saying which tokens or patches here are going to be getting a lot of weight to make my decision. Okay, and then I'll report that that's green because the token code vectors will have represented some information like the color of the token. Okay, so this is going to be a little too much detail to fully understand in just a few minutes, but here's the most common kind of attention layer, just to show you the mechanics really quickly. The question submits a query that is matched against a key in the data that you're querying. So the data you're querying is a set of tokens, and each token has a key vector, which gets matched against the query vector of the question. You compute the dot product to get the similarity between the key and the query. And that dot product, that similarity, becomes the weight that you apply to another transformation of your tokens, which is called the value vector. And you take a weighted combination of the value vector. And so all the fancy math here is just to say, the question will tell me which tokens to weigh heavily in a weighted sum to produce an output. But it'll be via these three transformations of the token vectors, which are the key, the value, and the query transformations. Okay. So that's a little mechanistic detail. We can go back to that if we want to discuss the nitty-gritty. But the way it kind of looks like is this, and this is common to most of the transformer architectures. You have a bunch of, you break into patches, then you have a bunch of layers, which are basically these one-by-one convolutional layers. And then every now and then you have something that tries to mix information across space, across tokens, and that's called attention. And that is just the tokens based on their values, queries, and keys will decide what should I, which of the other tokens should I average together to produce a new representation in the output. So this head might attend, say, I should look at the other heads to decide how I can better recognize what's going on in this patch.
When you say one-by-one convolution, you mean a patch is a pixel?
A patch is, so you vectorize the patch, and then you do like one-by-one convolution across all of those tokens where the channel dimension is the token vector.
Yeah.
Okay, so here's MLPs, and then transformers are two changes. One is that rather than scalars, they have tokens. And another change is rather than having parameterized linear weights, they have data-dependent linear weights that are given by that special attention operator. And that attention operator itself has parameters that define the key, the query, and the value, and those are the learnable parameters of the system.
Philip, just a small detail, but you start with self-attention and then you have a one layer, multi-layer perceptron. But in the previous slide, you had the opposite order, is that?
Well, so it'll vary a lot between the different architectures. Like, yeah, you could alternate these in different orders. And I did gloss over the detail of this is attention from an external question, but the more common thing is self-attention, where attention is coming from the image itself, from the data itself. And that's, okay, this is like attention from the question branch, but I could just have the data choose what in its own token sequence to attend to. Each token chooses which other tokens to attend to, and that's called self-attention. That's like this picture here where this patch will decide what to attend to get a better representation of that patch, essentially. Okay, so this is self-attention really, as opposed to, that's why the the dependency of the weights on the data is like this. It's attending to itself as opposed to attending if it's not coming from some external source. Okay, so I think this is the last one, just to connect it to one of the most common demonstrations of transformers is to do sequence modeling. But really transformers are more about set to set operations, but you can represent a sequence as a set, so it's fine. Oh no, I think I got the wrong slide here. Let me pull up the right one. Yeah, this is what I wanted to show. Okay, so here's how it looks for doing next word prediction. And you can do next, protein prediction in a sequence of proteins, or next sound wave prediction. You can do next anything prediction. That's a really common framework. So this is like a 1-layer transformer. We're going to say colorless, green ideas, sleep. Put that into the transformer. We want to predict the blank. The words attend to each other. Then you pass through this token-wise nonlinearity, and then you make a prediction at the very end. So just one example of what you have seen as transformers for sequences, but really transformers are more general than that. They're not just about sequence modeling. This is just one way you could use them. Okay, so that's the 10-minute overview of transformers. Let's see, should we do questions, or Brian, do you want to just jump right in?
Maybe you can do questions while I set up.
Yeah, questions while Brian sets up.
What is the history of these terms, quest, query, value, keys?
Probably other people here know better than I do, but I think it's all coming from the data retrieval database literature. So you have a database where you have knowledge stored in kind of cells, and you can query that database. So you say, I want to find things related to giraffes, and then every cell will have like a label, the key. It'll be like, this is a cell for mammals, and this is a cell for giraffes, and here's a cell for plants. And you'll match the query to the key, and then the stuff inside the cell that you retrieve will be the value. So I think it's coming from that.
Yeah. This isn't like a fully formed question, but I guess like in the framework of having question key value, if let's say the question was like, what is the color of the turkey's head? And for some reason, the turkey's head is like a feature that's complex enough that it can't be like well represented within a single token. Does that like cause issues with like attending to the right thing or like weighting the right thing properly when?
Yeah, I suppose it could. One answer would be that you often do multi-headed attention, where you'll take your sequence or your set of tokens, and then you'll have k different query vectors and k different value vectors and k different key vectors. And each query can be asking a different type of, you can say, I want to match to the same color. Another one can say, I want to match to the same geometry. And when you optimize the parameters of this network, it will somehow self-organize that. Well, if it's useful to factor things into geometry and color, then there'll be one attention head that cares about color and one that cares about geometry.
Just one quick thing on the transformer architecture and the non-linearity. If I recall correctly, you do a normalization of each token, right? What's the intuition for that? Why do you do that? I haven't seen that too much before transformers.
Yeah, that's a great question. So normally you want your weighted sum to add up to 1. So the weight should add up to 1. And people do that, achieve that via the softmax over the weights.
Yeah,
is that what you're referring to? Yeah.
No, I'm referring to post the residual connection. You do as part of the right before that.
Oh, the layer norms.
Yeah.
So, okay, my understanding of transformers has progressed to the level of tokens and attention, and all the rest, layer norm and residual connections. At this point, I don't grok it. I don't know why. That feels kind of like tricks that usually help neural networks train. It's good to normalize things. It's good to have residuals.
Yeah.
I don't see anything. I haven't understood anything specific to transformers about those ideas yet.
Okay,
They're generally useful tricks.
Okay, yeah, I got you.
Transformers are very hard to train, especially like several layer ones, like 12 and up, if you don't have like residual connections or layer norm.
Yeah, okay.
I think the training isn't very stable unless you put those tricks in.
So it's not, yeah. Okay,
Also, this attention is doing multiplication, and that might not be as stable as normal non-intentional layers just do addition.
Right.
Yeah, no, that's the softmax, right?
And the softmax can probably help with that.
Yeah.
So how do you decide what patches to use? For instance, in the image or in the text, you also had like what seemed to be arbitrary
Yeah.
segmentation of the data.
Yeah, that's a great question. How do you do the tokenization? Like, how do you design that? I think it's super hacky right now. So that feels like somewhere that people could do a lot of work. One thing that does seem to happen is that the smaller you make your tokens, if you have tokens that are a single pixel, it's just the better you get. So maybe what will happen is we'll just stop having clever tokenizations and just go down to whatever the atomic units of the data are, like a single character, a single pixel, and that just makes the choice for us because you can't go below that really. So I think the smaller in vision transformers, the thing I've seen is that the smaller the tokens are, the better they tend to perform. But because the attention mechanism is every token attends to every token, it's like n squared. If you make the tokens too small, there's too many tokens, and then you run out of memory. So there's probably clever tokenization schemes like superpixels or segmentation, or in language there's a lot of tokenization schemes that are like byte pair encoding is the name of one, and word2vec could be you could use that as your first tokenization layer. But yeah, that feels like a kind of hacky area right now to me.
We try to usually leverage at least some degree of topology by
Yeah.
tokenizing it that respects, spatial coordinates for images or
Yeah.
language order for words, at least. Because there's also something called position encoding, which gives you knowledge about the topology of why this element is in this position versus this other position. And that tells you a lot about, the structure of the image, or at least where this token is with respect to the overall structure of the image.
Yeah, and then another thing that seems missing right now is people usually in vision transformers, which I'm most familiar with, they usually break into non-overlapping tokens. But we know from ConvNets and signal processing that you'll get a ton of aliasing and in the filtering operations. If you have these huge strides, you're breaking into non-overlapping patches. You really would want to have overlapping patches or blur the signal. So all of that signal processing stuff, I think has been kind of thrown away. And probably it's a good idea to put it back in there.
Someone has tried overlapping patches,
Okay, I guess people,
and it does help, yeah.
And by the way, everything I say, as you probably know, there's 10,000 transformer papers now. So I'm sure everything that you could imagine has been tried. Yeah.
So the part about working with sequences versus sets confused me a little bit, and this relates to position encoding. So I think it is important when you send these tokens to the transformer to actually inform it where it is in the sequence. So so a transformer operates in sequences or sets, I'm
Brian, do you mind if I take the slides over one more time?
Sure.
I do have some slides that I think clarify that. So, yeah. So there's this idea of positional encoding, which I think is the third big idea of transformers, but it's been used in other contexts too. So maybe it's not just about transformers, but if you have a ConvNet and you don't want it to be invariant to shift, because convolution is shift invariant, you can just tell the filter where you are in the image by adding this positional code. So I can just say, at the bottom right of the image, and then my mapping will end up being conditioned on the position. Transformers, it's the same thing. I can tell you where the token comes from. And if you do that, then you do get sequential, you are modeling the sequence because you're telling the token, I'm the first item in the sequence or the second item. If you don't do that, then you have the property of permutation equivariance, which is why I said it's really a set to set operation. So if you don't tell the tokens where they come from, you don't give them positional codes, then if I take the tokens on the input layer and I permute them into any order, I will simply permute the tokens on the output layer. The mapping will be the same up to permutation. It takes a little thinking to see why that's true, but essentially the reason is because the attention layer is permutation invariant, because the way attention works, the way self-attention works is it looks at the color of this and the color of that, and it makes some similarity comparison. And then the weight of the weighted sum that goes to here is just going to be something about the similarity between the color, the query, and the key of this. So no matter where you move that edge around, as long as the input and output are orange and blue, it will get the same weight. So you can kind of work it out and see that attention is permutation invariant. The token-wise operator is point-wise, so that's permutation invariant too. And then that means that the whole transformers are permutation invariant function. And you can make it model sequences by telling it the position of every token in that set. But if you don't have position encoding, it's more appropriate for set-to-set mapping.
One more question or comment is, you started with the idea of tokens, but just a few sentences before you said that something that to me sounds like the idea of tokens is rather weakened, that the transformers work better when you have individual bits of data like pixels. So it feels to me that the idea of tokens is not really essential in the whole concept to work, but attention is the most critical part. And the idea that being able to attend dynamically anywhere in the picture, if it is visual data, is the idea that gives power in these algorithms, not the token per se.
Yeah, I don't know. And I think that's kind of the open debate. It'd be, fun to keep discussing it. So I think the field is kind of split right now between people thinking that it's the tokens and the vector, encapsulated vectors that are important to this versus the attention. And really, okay, if you just have an intentional mechanism, it can still be operating over neurons. It doesn't really have to be about tokens. I feel like both probably are important to the success. But one counterexample to that attention matters is there are these other architectures now, sometimes called like NLP mixer is one architecture in this family, which uses tokens but not attention. So it's basically a ConvNet over tokens, one-by-one comms over tokens. They call it MLP, not comms, and that's super confusing. But anyway, forget the terminology because these things are all just like small transformations of each other. Okay, but anyway, this MLP mixer thing doesn't have attention, but it's still, in my view, is a token net. And that seems competitive on some tasks with attention networks. So maybe attention is, maybe it's not the thing that matters.
Related to this question, so it seems like, especially in this self-attention mode that you're describing,
yeah,
if you unrolled that, it's like a series of matrices, I think, going on there that could just be implemented as a straight up feed forwards chain. If I'm following you, is it just very deep? You know, there's going to be skips, I think, but could you? Does that idea make sense to you? So
you can always kind of you can always take any one of these arrows and just say, oh, that's actually just a matrix multiply.
Right.
But it's a matrix with special structure. It's not like a full rank matrix. And I think that that's one way of just understanding all the power.
Of course, I didn't mean it was any matrix, but I'm just like, you could re-express this as another, as I was trying to understand what the re-expression form might look like and then generalize that to, and then you're back in standard mode again. Maybe that is closely related to what you were saying.
Yeah. Yeah.
Where you have the second branch with a queue, that's different. That's sort of active state versus this kind of deterministic processing based on.
It's kind of multiplicative there. And I think that's where like it differs from like standard MLPs where they don't have this kind of multiplicative interaction. That means that, you know, you're dependent on the own, you're self-contesting yourself, meaning that you're dependent on your own input when you process this particular input. So it's kind of like a hyper network, I guess, in that case, where like you change the representation based on what your representation already is.
Yeah. So it's not like, you can't just rewrite it exactly as these linear combinations on like a regular feed-forward network, because it does do these multiplies. Maybe that's the one mathematical atomic unit that's different. But I think you can express these in different languages. And I actually do like thinking of it as, it's just a special kind of matrix. The matrix weights come from this other source, this self-attention mechanism, but then it's just a matrix. But that matrix has special structure, and understanding that low rank structure is kind of that's just a way of understanding architectures, is what is the special structure you're imposing on the linear transformations on the matrices. But yeah, this dot product here between the query and the key involves multiplication, which is not something that you would directly get in a regular network.
Maybe somewhat related to this, and also the permutation equivariance, that's within a block. So what about across transformer blocks?
Yeah, so you could have, you can kind of have any set of tokens attend to any set of tokens, and they could come from one layer of the net and another layer of the net, or one block, another block. It could come from a text processing network and an image processing network, and then the text attends to the tokens of the image. And then it could come from just the text tokens attend to themselves, and that's most of what I talked about. But actually, sorry, did that answer? Is that your question, or am I gone the wrong way?
You said that you could commute like within a block, like the operations.
Yeah.
Pretty much. Like I'm just saying, if you have like 12 transformer blocks, it's been shown that some of the earlier blocks like learn more like surface form type of features, while like later learn
Oh, yeah.
more like high level things. And I was wondering about like, can you also commute?
Yeah,
blocks
I
and
think no, probably.
No.
So I don't think you can permute depth-wise. I think just you can permute within
within
the input sequence. Yeah.
Actually, with multi-headed attention, you know how they concatenate all the heads together to go to the next layer? Don't they lose the permutation invariance or the permutation equivariance when you do the concatenation process?
I don't think so.
Because your concatenation has to have some sort of ordering.
Oh, interesting. Yeah, maybe. Okay, so it's possible that transformers aren't
At least not
always
multi-headed
permutation
transformers.
equivariant.
The individual transformer heads are equivariant.
Yeah, I hadn't thought about the multi-headed thing. Okay. Yeah. Because in the multi-headed, you take a weighted sum of the heads, and then
The feature vectors they concatenate together.
and that's a parameterized
if you
sum,
don't-
and if you change the order of, yeah, I think you're right. Okay, interesting.
Philip, did anybody try, instead of using the Q and K matrix or the WQ and WK, use a single matrix?
Yeah. Okay, so one thing you can do is just get rid of queries, keys, and values, and just have your code vectors Z, and take like the inner product of, or the outer product of Z with Z as your attention. And I think that can sometimes work just as well. But I haven't really followed the latest on that, but you can have queries, keys, and values that are linear functions of your code vector Z, or they can be nonlinear functions, or they could be identity. And I'm not sure that there's a consensus on when you need which. So one thing that's kind of interesting is that if you use the identity to create your queries and keys, you're basically creating that gram matrix between all of your token vectors with themselves. So it's going to act kind of like, it's going to cluster the data. And there's been some analysis of how, okay, identity, attention, identity queries and keys will create this, clustering, like spectral clustering type matrix. It'll create this similarity matrix. When you hit the data with that similarity matrix, it'll group things that are similar. And maybe we can understand a little bit of what's going on from that perspective. Like linear queries and keys are just some projection of that kind of thing.
And how does that work if you don't have the WQ and WK matrix, but just the identity?
Actually, yeah, do you know, Brian, or does anyone know?
So ResMLPs are actually kind of like this, more exactly like this spectral matrix, because what you do is you process the input, transpose it, process it again. And if you work out both operations in sequence, they end up becoming like Z transpose Z with like a matrix in the middle. So I think it does work, I guess.
Yeah, that was maybe not as well, but it does work.
I think it works, just maybe not as well.
Yeah.
Because you're still interleaving with these nonlinear operations, you still get expressive power.
And one other question that you mentioned, and there is a paper, I think, from DeepMind about using a single pixel as a token, right?
Yeah.
It seems very little in terms of being able to establish similarities with other tokens, because you have just color and intensity, right?
So my feeling there is that, yes, on the first layer, that's a very bad token. You can have a 1.8 dimensional vector that codes just the color of a single pixel. It's not going to do much. But then when you do this linear combination operation, it's like taking a 1x1 patch and making a bigger patch out of it. I mean, it can learn to mix information, across the whole image and say all of these similar colors. Maybe all the white stripes on the zebra will go with all the black stripes on the zebras because the black keys will match the white queries. So it could create these abstracted tokens as you go deeper into the network and build up complexity.
Many years ago in computer vision, there was the idea of, instead of using a patch, of using at a single pixel, the value of the pixel and derivatives.
Yeah.
Which means essentially you're having non-local information because the derivatives gives you information about neighboring pixel, spatial derivatives.
It's kind of like a little token, yeah.
So
A vector, yeah.
it was a
vector
vector of, and it's very much like a token, yeah.
Yeah. Yeah, so I don't think that these are new ideas really. It's just, it helped me to coalesce around the idea of a token. Like we're gonna think all the operations in terms of tokens, but we used to talk about, hypercolumns and feature vectors, and like there's a million names for the same concepts. Yeah. And Brian, do you want to pull up just so we have time for you too? Yeah.
You made a connection earlier with graph neural networks. I don't recall which one you said is more general of the two.
Well,
but I also don't feel the connection because for graph neural networks, it's important, like the connection in the graph, the structure is very important, whereas in transformers, you said it is less of a case.
So yeah, I think it depends how you define these things, but I like to think of graph nets as more a broader class. And so transformers would be graph nets with a fully connected graph. So every token talks to every token. And the aggregation function that decides how to do like the weighted sum of incoming messages is given by this attention operator. So the similarity between node A and node B tells you how much the messages from node B will be summed up into node A.
And you can have attention in graph neural networks. That's why you feel it's.
And that's, I think it was independently invented over there, or maybe even first invented over there. So GraphNet people have done attention, I think before transformers made attention really popular, although of course attention is an old idea as well, and it has shown up a lot of times.
So I guess I can start now. Yeah, Phil gave a great overview, which actually is going to make this a lot easier, where I think I'm going to go over more of the AI machine learning community's perspective of attention and kind of the developments happening in that community, and go over some kind of unintuitive things about transformers that I think are surprising, I guess, to a lot of people now. To go over that, let's kind of go over how it started. So originally, the transformer was a language model, and the language model paper had possibly the most arrogant title you could imagine, saying that attention is all you need. Now, little did they know that that actually turned out to be something that would actually have a little bit more truth to it than I think most people realized, including I think myself, which is that this now is a model that covers, as Phil mentioned, language, speech, vision. It's basically a universal model now for all the modalities that people apply to data, actually. And again, attention is not a new idea. This is something that was proposed even before this paper, but this paper proposed something that was very, very similar to the vision transformer attention, where they created essentially attendable feature maps at the last layer or the next to last layer of a VGG network that was still spatial. And they were able to use this to show that when you do image captioning, it would attend to the correct parts of an object. So the reason why I think this kind of seminar is important is because classically, whatever works well has always been something that we always ask ourselves, is the brain also doing this? Because that's been the classical thing for a lot of the past, 10 years of research, actually a lot from Jim McCullough's group. And I think we have to understand what's going on, I think, to understand why transformers are so important and potentially why we should either care about them or not care about them, actually. But I think there's this all too familiar aspect where whatever is working extremely well, we need to compare that to the brain now. And I think we should kind of get ahead of it this time because in this case, we want to see where they're going. And again, one of the things that's kind of interesting is that when people compare these attention models, specifically certain versions of them like CLIP, to human behavior, you get a substantially improved performance in terms of like explaining either the misclassification errors or not in human visual systems. And I think the issue is like, we don't know why this is happening in the sense that like in this paper, they mentioned that the particular vision transformer model that they tested was far better than all their other models for explaining human behavior, but they weren't sure why at the time. This was from a 2021 paper, so I believe that they're still not sure, but all they found was that the results show that this particular model CLIP was an outlier for their comparisons to human behavior. And also there's been, like I said, this natural tendency to now compare convolution networks to transformer networks because the transformer networks are starting to outperform ConvNets on a lot of vision tasks. So the question is now, which models are more similar to neuroscience or just human vision in general, whether it be cognitive science as well? Are ConvNets more similar or transformers more similar? And intuitively, you would think that there are certain properties of convolutions that make convolution convolution and transformer transformer. And what makes what we believe convolution a convolution is the fact that of equivariance. Meaning, as Phil mentioned, when you apply an operation to the input, the operation applied to the output should be the same type of operation. Now, the issue is that this turns out not to be exactly true. It turns out after training, a vision transformer is more equivariant to translation than a ConvNet, which I think is quite surprising. So Phil might actually already know the issues with the convolution not being equivariant. One thing being that a lot of the pooling and other operations, even the nonlinearity, contribute to hurting or harming the equivariance performance. So this plot here is showing by this paper's measure, which is a Lie derivative, the equivariance error of a ConvNet, this is ResNet 50, versus a vision transformer. And it turns out after training, a vision transformer is translationally more equivariant than a ConvNet, which I think is quite non-intuitive in the sense that we built in the equivariance specifically for a ConvNet. Yet here we are, and vision transformers are more equivariant after training. And then this plot on the right shows this is not just specific to these two architectures, but many different architectures here. And it's also interesting that they also measure MLP mixers, which, as Phil mentioned, is kind of a new architecture also, that also has surprisingly high equivariance after training. And this equivariance improves as you increase ImageNet test accuracy. Does anyone have any questions here?
Brian, one question. Do you have positional encoding on these networks?
Yeah, you do have visual.
So it shouldn't be equivariant.
Oh, well, this is like a measure of the equivariance.
Yeah, no, I mean, it shouldn't be like.
Oh, it shouldn't be, yeah, it shouldn't be.
We have to learn to be.
Well, in that case, equivariance is very strictly by the patch. In this case, they're doing small transformations.
Oh, I see. Okay.
So it's not the size of a patch. But since you asked that question, there's another paper that shows about invariance. And this is like much larger translations. And they show that actually after training, a trained vision transformer, which is a transformer model, is as invariant to translation shifts as a ResNet 18, which is a ConvNet. And this is kind of interesting because then the question is, what's going on here? Like, we build in these things to our models, but apparently not building them in also gives us the thing that we wanted. And I think this kind of goes to the issue that maybe might be controversial, but has been kind of true, which is the idea of scalability. And are people familiar with the bitter lesson here? Or has anyone heard of the bitter lesson? This is like a classic controversial statement. Actually, I think a former professor here actually gave a retort to this thing by Rich Sutton, who wrote that the lesson that we should take away, and this was written, I think, in 2019 or 2018, is that we should not be working on inductive biases for models as much as we should be working on inductive biases for learning. And I think one of the kind of key directions that organizations like OpenAI are going towards is the idea that we shouldn't really try to bake in these priors that we think are really, really useful, because at some point your data might give you that prior anyway. And that could be what's happening here. And to give you a flavor for what's going on in the machine learning community, they're essentially optimizing the upper right-hand corner of this curve. And the x-axis here is the compute required to train these models. And the y-axis is the negative log perplexity, which is essentially the task error, or task performance, I guess, not error. And in this case, what they're doing is they're trying to find architectures that go all the way up here in the performance curve. And they're essentially paying for that performance, not by incorporating inductive biases into their model, but by trying to absorb those inductive biases through data. So I think to give you a glimpse of what's happening in the future is that there probably will be less inductive biases in this community of machine learning because they're willing to pay this cost of compute to not have to build in the inductive bias that they would normally have to build in for smaller data sets. And as Phil alluded to, which is or as actually Tommy also mentioned, which is these architectures are getting more and more general purpose. So in this case, this is a transformer architecture, but unlike a transformer, this is an architecture that can attend not over the token level, but treats each pixel as a token. And what's interesting about this is that they actually trained this on ImageNet without any image prior. So the position encoding that Phil mentioned was actually learned by the model, and they could actually get performance on the order of, normal image prior oriented models like ConvNets and, patch vision transformers. So the remarkable consequence of this is that there's no actual image prior or modality prior built into this model. It learned it on its own. And even in that perspective, it's still competitive on ImageNet. So this is not necessarily a very large data set either.
Do you know if the perceiver, Brian, also has like a texture bias, for example, or if in general robustness?
I don't think they've looked into that. I think the robustness qualities are probably not too different from standard trained models. I think in terms of adversarial examples, like transformers are, well, I think it's controversial, but I think people say transformers are a little bit more robust adversarial examples than ConvNets, but on the grand scheme of things, they're both very susceptible to adversarial examples.
I mean, just to finish, I was just curious to see if, I'm sure there's many models now that they can all do whatever, 75% on ImageNet, but not all of them will see like a human, whether that's a goal or not, right?
Right, that's a good question. And I think like we have to now be aware that this is where the field is going.
Right.
Is that where we're going as well as a field? Not, yeah.
What does it mean to learn position features in the case of an image?
So you randomly initialize the position encoding to be just from like a random Gaussian or something.
Position of the pixels in the image, so it's like an unordered set of pixels?
Right, so you treat each pixel as an unordered element in a set.
Wait, but Brian, isn't it the case that the top left pixel will always get the same positional encoding? It'll be learned.
Yeah, so it's not like you can shuffle every image independently of every other image and then get.
So I think it's still inserting a lot of information there.
Well, the prior that they're inserting is that the topology is consistent across samples.
Yeah.
Which I think is reasonable about modalities mostly. Like you would imagine that the position shouldn't be unique to every single sample, because in that case, then I think the problem would be almost like really, really hard. I don't know if you can even learn anything besides
if you randomly shuffle all the pixels in an image, there's no.
Yeah, I don't know what you're going to be able to learn. Yeah. Every image has its own permutation that you give it to the models. You could learn like higher like statistics, I guess, over like all the pixels together. Yeah.
Another number is how many training example it takes to train this compared to a convolutional network.
Right. So I think one of the things that we know is that it takes more data to train a vision transformer.
But you have the number for this?
This is, I think, just ImageNet with augmentations, actually. This isn't like a larger data set. This is just augmentation providing the extra information.
I think, I don't have the numbers, but the cursor I've seen tend to be, we have a whiteboard. So the ConvNet starts here and goes kind of flat, and the transformer starts down here and goes up. So it scales better, but for low data, it's doing worse.
Right. So I think that's one of the things that why the community is going towards, like industry especially, going towards this direction, because they're willing to pay for the scale via compute cost rather than having the kind of built-in data points, I guess, be not, for free, I guess. Because like what happens is that convolutions, after a certain level of scale, will start saturating, and transformers still continue to go up in terms of increasing the parameter count will give you still positive returns in performance. And then what I didn't discuss in this talk is also, there have been a lot of other variations of transformers as well. And it's kind of strange, actually. People have, at least Google has done a meta-analysis on transformers and all the zoo of variations of them. And at least in terms of scalability, it seems like the original transformers actually scales the best, which is a little bit odd.
Which one scales the best?
Vision transformers. Well, there's vision transformers and also sparse mixture of expert transformers. Those apparently both scale.
VAT though.
VAT. Well, don't remember if they were specifically doing vision in this case. I think it was more language tests. But I think this kind of tells you a story that maybe the machine learning community is going towards, which is not, the fact that architecture matters the most, but the fact that data is actually the really important aspect. And I think they're building now architectures that aren't necessarily good at working well without, being trained, but furthermore, work well at absorbing data a lot more efficiently than other architectures. And I think we should think about the things that lead to the resulting model that we work with these days, which is the idea that it's not just the model itself with its architecture, but there are priors about, the compute, the capacity of the model to train over that data. And also more importantly, now more recently, the nice thing is that as Phil mentioned, the notion that a lot of these models don't require supervision, so they can absorb larger and larger data sets without much economic cost to the person training it. And another aspect of transformers is the way it was created was mainly as an alternative to recurrent networks. And the reason for that is because, as you see in the left arrow, I mentioned hardware. And one of the things about transformers is that they're much more parallelizable on GPUs than a recurrent network is. And they run much more better on stupidly parallel software than a recurrent network does. And that's why they become very popular also, is because the parallelization of them is much easier than other sequence models.
One comment, if I may make, how I view this. I feel when you go to transformers, just by introducing the idea of attention dynamically handled by the data, you kind of have, it's an overstatement, but as general architecture as you can have, you have really powerful architecture, and now to train it, you need a lot of data, and this is really where we are now. And more data does better, just because the architecture is extremely general, much more than convolutional, as you said. So I don't know if there will be any other fancy architecture that would be more general.
Maybe two comments on that. One is they are lacking one thing, which is vanilla transformers don't have memory. They don't have feedback connections. And so they're not Turing complete in the same way that an RNN is. Of course, people are adding memory and recurrence to transformers, but still the majority of them don't have that. So that's actually, I think, a big limitation. They don't have memory. And then two is, eventually lookup tables will perform best, or nearest neighbor will perform best, because in the limit of infinite data, those work, and we don't know if these work in the limit of infinite data. So yeah, I agree. It's not surprising that you need less structure with more data.
Brian, you were saying there's choices to be made for if we're interested in models of brain systems.
So the question is what are we interested in terms of if these architectures become less biased towards being structurally more relevant to neuroscience, but just being more task relevant to neuroscience? Are we going to be stuck at some level of understanding that's only functional?
What makes them structurally less relevant? That's sort of why I was asking these kind of weight questions, right? Why do you say that?
Well, so I think that the tricky part is I think because things work well, people will find ways to say that they're more structurally relevant. I don't know if transformers are more structurally relevant than CompNets. Obviously there's the Fukushima, neocognitron, which is inspired by neuroscience, but attention themselves was never inspired by, or at least transformers was never inspired by neuroscience. So I don't know if they're actually more neuroscience friendly, I guess, in the terms of similarity. But I think what the bigger picture is that they're going to be more and more generic, and they're going to take less inspiration from structural biases that we know about necessarily, until Phil mentioned the idea of recurrence and feedback, and those things become more. Because actually one thing that's interesting is that there hasn't been much. I mean, people have proposed these architectures and they do work, but people aren't really using feedback versions of transformers, mainly because there's no recurrent nature to them. So for example, all these things are still feed-forward architectures that still process from the bottom up. But I think the divergence is going to be are we going to be interested in the same models that the AI machine learning community is going to be interested in? Or are we going to be interested in specific models that work well in neuroscience, but don't necessarily have a functional performance equivalence to what these models have?
One question I have for the neuroscientists in the room is, what is the scale of data that the human brain is trained on when they reach adulthood? And my rough estimate or understanding is it's similar to what the biggest transformers are currently trained on, or a little bit smaller than that, but much more data than ConvNets were trained on. And so all this stuff about how, in which data regime do you get what kinds of performance? Well, the data regime that seems most relevant to neuroscience, to me, seems more like this transformer regime. But I don't know if that's true. Like, how many images do humans see compared to these models?
That's not true for text.
Text, I think they're trained on much more data. But for
human
I'm thinking
could not
images.
possibly read everything on the internet, right?
Yeah.
But there was a paper from Fenderenko's group recently that showed that even if you train a GPT-2 on a 10-year-old amount of text data, it does explain fMRI responses almost as well as even having a lot more data.
That's because fMRI is bad.
Oh,
So the finding is training a transformer on around 10 million tokens, which is like what a child would be exposed to until the age of 10, while like most transformers are trained on like many billions of tokens. And it predicts fMRI data around equally well. But fMRI has its own limitations.
But there's an assumption under this question, which is like, are we actually interested in models of the system in the adult state, or are we interested in models of how the system gets to be in the adult state? Those are not the same question, right? So there may be a shift here between models that are like, and you sort of called it out, like, hey, we can, instead of us having to hand design them in, this is the bitter lesson version, we'll just lean on the data with a general flexible thing and let the data push it as long as our compute can handle that. We have enough data. And I think the question you're asking that's sort of interesting to us, at least some of us, is does that end state, which of those end states looks more like the adult end state? That's agnostic to whether, neither of them probably followed the same biology path, but just even in that assumption state, what is the state of affairs? I don't think we know what the state of affairs is with visual transformers relative to ConvNets on alignments with even visual processing. I mean, somebody was asking here about somebody here was asking about similar to humans, maybe that was you. And then because also at the neural level, it also requires mapping assumptions and they get more complicated with the transformers, right? But behaviorally, it sounds like, in the Garrio's paper you were pointing out, like there's some maybe better alignment, but I don't know how they compare against the latest, AT trained, ConvNets,
So, I don't know about, I think those studies haven't been done to my knowledge of like actual alignment with neural recordings. And of course that, I'm sure people here will do that. But alignment in terms of functional capabilities does seem quite a bit better, just anecdotally to me, because, ConvNets, what can they do? And what's been demonstrated with ConvNets of 10 years ago, classify 1,000 animals, cats and dogs and image categories. Well, sure, you can make ConvNets that grow bigger, but the current generation of the best models are these transformers, like CLIP, but of course there's a CLIP non-transformer version, but let's just say CLIP. And that seems much closer to the functionality of the human visual system, that you can recognize millions of categories or way more than thousands of categories. And you can recognize compositions of categories. You can type in a red ball and have recognize the red ball and just see one example of that. And these networks are getting to that point. So at the kind of psychophysical level, I think they're getting closer. I don't know at the neural embedding level.
So something that I'd like to share is there was one paper that me and William, a co-author, wrote that we submitted to NERDS. It actually got rejected, but it was one about, and we just resubmitted Isola about this transformer model that achieved state-of-the-art in brain score for area V4, which is kind of interesting because we went to the brain score competition at the beginning of this year, like just hoping to participate. And all of a sudden, William trained this transformer. It was a dual stream transformer with adversarial training and rotations. And we just broke the record in V4 unexpectedly and wrote a paper about that. In any case, what I think was interesting is that the same model, exact same architecture, if you trained it another way, just classical SGD, ImageNet, no fancy augmentations, adversarial perturbations, the score wasn't that great. So I wonder, just in general, should we also just be thinking about transformer model or the interaction of transformer models plus any type of training regime, or maybe a fancier loss function that we haven't even conceived? And suppose we do hit the explain variance or one correlation in brain score for IT, like how do we even reverse engineer from that, right? Because the model is just so big. I'm saying playing devil's advocate on my own work, right? Like the model's so big, like how do we even go back? And it's an open question, you know, just I don't know if anyone has any ideas or.
If anyone else.
I mean, I think one of the things that I think we often forget is that a model isn't just its architecture, like, you know, the slide before. A model is also data. And once it's interacted with data, we have to understand data now too, to understand what that model is doing. We can't just understand the architecture. And I think as these models become, or these architectures become more generic, data is going to play a larger and larger role. And we're kind of back to now trying to understand data now rather than understanding what the architecture is. And I think that's, I don't know if that's easier or harder.
But also the message is, you know, for the last 10 years until transformers came, like 3 or 4 years ago, I think the success stories in deep machine learning was convolutional networks. There was one architecture. Now there are several. And so we have quite a few options. And, you know, they all perform pretty well.
Yeah, so
and I think if you just compare functions, input, output, or how well they fit neurons, you'll find they're all doing okay. So you need a lot of other constraints, which means what can be implemented by neurons and synapses and what cannot, or very difficult to see how.
Yeah, I agree, and I gave this guest lecture in Tommy and Brian's class, and I was calling it the Anna Karenina conjecture that like as systems get more and more intelligent, they kind of converge on the same representations, abstractions, models, and so forth, which other people have put forth. And I think it's kind of the same here. I don't actually think the difference between transformers and confidence and MLPs is that dramatic. I think it's more as you get more and more data and you optimize more and more toward success at some objective, the models will converge.
Well, that's one way, but the other way is the, you know, what I said at the meeting a few weeks ago, it could be like flight, you know.
It could be.
Yeah, you have a, you know, a model of a bird, but that's not really good for everything. What is important is to understand the principles of aerodynamics. Then you can understand how birds fly and how to build airplanes and other things, and maybe how flies, which is different from birds, because the aerodynamics involved is different. So I think principles are much more important than the specific implementations, which can be quite different. And the question is, what are the principles here?
Yeah. Yeah, and I think there's similar principles. I think
principles,
all of these architectures are like just reweighting of the same few ingredients. Factorization is in all of them. Hierarchy is in all of them, right? Like, I don't know. And even in transformers and confidence, like transformers can be rewritten as 90% convolution and just a few little layers that are attention. Like if you look at the actual operations, almost every operation is a convolution in the sense of being a one by one, chop up the signal into patches and process each one independently and identically. Yeah, so I think the principles are going to turn out to be very similar.
And the question is, which principles should we care about now, given this kind of heterogeneity in architecture, but similarity in functional performance? Because I think one of the things that it becomes easier if the community like has something they cannot do, whether it be like, you know, to fly, I guess for the example of flight, which is like, how do we achieve something that we can't currently do right now? I think the general spirit of the machine learning community is that, oh, we're done. We can just keep making these models bigger, we can keep doing this and we'll be fine. But I don't think that's true. But right now, it seems like the spirit is in that direction. And that's why we're kind of revalidating, oh, of course, this must be like the brain. Of course, this is like what we care about. Of course, all these kind of back explanations are working. But once we hit a wall, I feel like then we know what's wrong and what's correct. Otherwise, I guess it becomes kind of hard to tell right now.
On the topic of like data efficiency, this might have an obvious answer, but like, I was wondering if, in like, when you have multimodal data, whether like learning becomes a lot more efficient if you have like X bits of information from visual stuff and X bits of like texts that like maybe are captions associated with the image or something versus like 2X bits of just like text data and then you do some like.
I don't know how well those things have been estimated, but the language vision models are a lot better on certain benchmarks than the vision only models. And it does seem like language must be like incredibly valuable per word. There's a lot more information than per pixel. So it seems like a lot of the recent success is just leveraging language, at least in computer vision. And same in robotics, a few other areas.
I think what made CLIP a lot more, at least from that psychophysics experiment from Garris et al., a lot more like powerful for their results was the fact that CLIP was trained not on classification, but on caption similarity matching. So matching to a text caption, which has a lot more information in the caption than just a single label for this entire image. Like caption can tell you, things about geometry. It tells you what things on the left, what things occluded, what thing is, what season it is or what time it is. Like it tells you a lot more information than a single word would be to ImageNet class.
Okay, this is a little anecdotal, but what I've heard is that for training diffusion models, if you train them without language, just unconditional diffusion model, generative model of imagery, it's really expensive. And we all thought like, okay, we're not going to get into that game. It's not for us, it's for Google. But if you train them text conditional, they're actually much, according to the students I've talked to, they train much faster because the text conditional models, the text gives you so much leverage. And so they said that, no, we can train text conditional, like, DALL-E type models, stable diffusion. Those things are within the budget of MIT.
How do you do that to train conditional?
Because you have to have text image pairs. So you have a lot, this is a huge source of supervision there, as opposed to just random images. And if you have that, then you're in the hundreds of thousands of dollars of range to train one of those big models, as opposed to the tens of millions of dollars range. This is anecdotal, what the students are saying right now. They might be just trying to get some GPUs, I'm not sure.
By the way, just a question to both of you, but an important feature of transformers compared to previous networks is the fact that you don't have to worry about labeling, especially when you use text, right?
Yeah.
It's
right. Well, I think that's the issue about the definition of supervision, which is like, I never found a consistent definition of what a supervised task is versus an unsupervised one besides economic cost. Like how much did you spend to acquire this data? It seems to be the only consistent label.
Well, but if you speak about neuroscience, it's not only cost, right?
Right, but then like, I think, this is another divergence then between two communities, right? Which is like,
But the real problem is the brain, come on, everything else is.
Cool. Any more questions? I'm happy to keep chatting. I'm not sure when we're supposed to end.
I think we went for quite some time. We can adjourn and to the next iteration sometime in the next few weeks. Okay, thank you, Phil.